Alright, this is going to be a quick video on impulse and momentum. So we talked a little bit already about some of these, impulse and momentum, in class. So we figured out that impulse has this lovely letter J, so we're going to call it Jimpulse. Jimpulse is force times time. We know momentum is mass times velocity, and remember, momentum is technically that Greek letter rho. Wow, that was really bad. Greek letter rho. There we go. It's a Greek letter rho, but we know we have kind of simplified things a little bit, and we're going to just use a lowercase p for that. Then you can put these together and say that J, we figured out was, say mass times final velocity minus mass times initial velocity, which can be looked at as just, hey, change in momentum. Some initial final momentum minus some initial momentum, and that's change in momentum right there. So we can say, hey, force then would just be change in momentum over change in time. And that's all coming from, hey, if this is change in momentum right there, divide the t over the other side, you get force is equal to change in momentum over change in time. Now this is actually Newton's second law. That is how Newton first published his second law. He said that force was the change in momentum over the change in time, not the standard F equals ma that we see now. But it says the exact same thing, because remember, this is just mass times velocity. Velocity divided by time gives you acceleration. So we've seen all this kind of stuff before. So what this is all going to be about is, how can you solve some problems with this, or how can you analyze a situation like this using momentum and impulse? So let's just dive right in. If we have a 2 kilogram object that is moving at 2 meters per second, is subjected to a force. So, okay, force. Force occurs. Now, whatever that force is, it could be a baseball bat, it could be a tennis racket, it could be someone's foot, it could be you punching it, doesn't really matter. There's a force. And then you have this object over here, still 2 kilograms, and now it's all of a sudden moving 6 meters per second. We want to know what the change in momentum is, or another way of asking it would be, we want to know what the impulse, what the Jimpulse is of this object, or delivered to this object. So we know that Jimpulse is change in momentum, so all I have to do is figure out how much momentum it has finally, or on the after side, and subtract off the initial momentum on the before side. So you would calculate that by doing 2 kilograms multiplied by the final velocity, 6 meters per second, minus 2 kilograms multiplied by the initial velocity, 2 meters per second, which comes out to be 12 minus 4, which gives you 8. And what unit are you going to use? Well, we have seen that momentum is a kilogram meter per second. What Jimpulse is technically a change in momentum, so we're going to say a Newton second, 8 Newton seconds of impulse. Kind of like way back in the last unit where work was measured in joules and energy is measured in joules, and work is technically the change in energy, not energy itself. We're kind of doing the same thing here. It's just now impulse, which is a change in momentum, has its own unit, which is technically the same as momentum. We're just going to call it a Newton second. All right, now let's say that force occurred over a time period of 0.1 seconds, so 1/100th of a second. So how do we figure out how much force there was? Well, we know force is change in momentum over change in time, so that would be 8 Newton seconds divided by 0.01 seconds, or 800. And you can see the seconds will cancel out. So that means it took 800 newtons, a time of 0.01 seconds, to get an object moving from 2 meters per second to 6 meters per second. Now you can think about it. That was a really, really big force, 800 newtons. So it didn't have to apply for very long, 0.01 seconds. If we had only used half that, only 400 newtons, then it would have taken twice as long. If we had used a quarter of it, say 200 newtons, it would have taken it 4 times as long to get from the 2 meters per second to the 6 meters per second. But we know that impulse and momentum is not like energy in the fact that it is actually a vector. So what if we took a look at pretty much the exact same situation? 2 kilograms object moving to the right 2 meters per second. Okay, there's our force. Okay, force happens. And now, all of a sudden, instead of the object moving to the right with 6 meters per second, it's moving to the left with 6 meters per second. So just looking at it, we can already see that it's actually going to have to be a bigger force, right? Not only are we're not just increasing the velocity that's there, we have to subtract off 2 meters per second, stop the object, and then get it going back the other way, putting it back up to 6 meters per second. With work, we didn't really care about that. All we cared about was what the initial energy was and what the final energy was and how much it changed. But with momentum, we actually do have to care about it. So our change in momentum would be 2 kilograms multiplied by 6 meters per second. Now there's a negative in front of that. Okay, that negative means something. Okay, what does that negative mean when you're talking about velocity? Well, it means direction. It means, hey, we're traveling in the negative direction. Beyond that, that's it. So it's just is negative. Then we're going to subtract off, because it is a difference between final and initial. 2 kilograms multiplied by 2 meters per second. And that 2 meters per second is positive because it's moving in the right direction or positive direction. So now we have a negative 12 minus 4. We get a negative 16 Newton seconds worth of impulse. If the same time period of 0.01 seconds was happening here, then we would have a force of negative 16 Newton seconds divided by 0.01 seconds, or 1,600 newtons worth of force. Technically negative. What does a negative force look like? If a positive force over here was a force making something go faster that way, or basically having an acceleration that way, then what would a negative force look like? Well, that's a force that's going the opposite direction. It's a force that was on the object going to the left. Now, we kind of figured out that that was going to happen, right? Had to be bigger, so it comes out to be 1,600 rather than 800. And it had to be going the opposite direction, because you have to slow down the object and then get it going back the other way. So it had to be going to the left rather than the right. So here's where we're really going to have to pay attention to how the questions are asked. If they're asking for magnitude, the magnitude of the momentum, the magnitude of the impulse, that means we have to calculate it knowing that direction is a thing. We have to make sure that direction matters, and when we do the calculation, things are negative when they're supposed to be and positive when they're not. And we come out with a number, but if it just wants the magnitude of it, we don't really have to tell them which way it's going, positive or negative. But we still have to make sure we calculate it using direction. This is also the reason why in your car crashes, the objects that bounce, right, those bumpers that we made, the bouncing objects, were the ones that ended up having higher forces, because they were the ones that came to rest and also went back the other way versus just coming to rest and kind of just sitting there. So the ones that bounce end up having more velocity because they have that change, or more change in velocity, because you had to stop it and then get it going back the other way. So you end up with more force there. All right, last thing we're going to go over is when we talked about work was force times distance, and we looked at a particular type of graph, a force distance graph. And let's say we just had some random graph over here, and we said, hey, if you calculate the area does a force times distance for you, and the area gives you work. That's your area. Well, what about our Gympulse here? Gympulse is force times time. So is there a graph out there that would give you the impulse by calculating the area? There is. If we were to plot force as a function of time and ended up having a graph, that area, all this area in here, would be, in fact, impulse. Gympulse. Because we're doing force times time. But these areas here are areas where you don't have a constant force. Your force is changing with time. And in fact, most forces change with time. Think about like a rubber band or a spring, even someone punching you. Okay, the initial force is much bigger, but as the punch elongates, it becomes less and less over time. So your force is not constant, while in this area it was constant. So the area underneath this graph is what is the important part. And remember, this was called the integral, which was a calculus word that just means area. So if you have a force versus time graph, like for those bumpers that we did, which is trucking along, trucking along, trucking along, then goes up like that, that's a little bit harder to find the area of, right? And this is where you would need calculus, or you would need your LabQuest. LabQuest can do that for you, which might become important at a later lab. All right, so there's going to be some questions for you, and let me know if you have questions.